Unit 1 Review, Problem 5. Part A. Construct a frequency histogram with an initial grouping of 336 to 338 feet for the data collected in Problem 4. The data collected in Problem 4 was the total stopping distance for a sample of 25 automobiles driving in dry conditions at a speed of 65 miles per hour. To make a frequency histogram with this data, or basically any graph, we first begin by coming up with a title. The title has to include the data that's displayed in the graph along with the population from which the sample came from. We need each of those things to help put in context for the reader what the graph is displaying for them. So again, in this case, since the data was total stopping distance, our title can communicate that by saying it's the total stopping distance. Measured in feet was the units. And the population from which the sample was taken was automobiles traveling at 65 miles per hour in dry conditions. So an acceptable title for our frequency histogram would be the total stopping distance in feet for automobiles traveling at 65 miles per hour in dry conditions. Now, to construct a frequency histogram, we need to draw a horizontal axis and a vertical axis. We also need to make sure that each of these axes are clearly labeled. The vertical axis is where we display the statistics we want to show. In this case, the problem specifically asks for a frequency histogram. So we label the vertical axis frequency, where we're going to display the frequencies. Now we can't write out the scale of frequencies yet because we haven't counted the data or gotten the frequencies, so we'll have to do that later. The horizontal axis is where we label the data. And since the data is the total stopping distance measured in feet, we label the horizontal axis total stopping distance measured in feet. Now we need to come up with the scale for the data axis. The problem asks us to construct our frequency histogram with an initial, that is the first group, of 336 to 338 feet. So the first group that we are labeling in our frequency histogram ranges from 336 to 338 feet. So the problem gives us our initial grouping, and now we need to complete the rest of the scale by finishing this pattern of groupings. To do this, we notice that the initial group of 336 to 338 feet is grouping the data 3 feet at a time. That is, you have 1 at 336, 2 is 337, and 3 is 338. So we need to make all of our groupings to fit this table by grouping them by threes, or making a class width of 3 feet. So to fill out the rest, we notice here, since the first group starts at 336 and ends at 338 feet, the next group needs to start at the next measurement over from 338 feet. So since it ends at 338 feet, the next group starts at 339 feet. And since we're grouping everything consistently by threes for total stopping distance, we include the 3 distances. 339 would be 1, 340 would be 2, and 341 would be the third. So our second grouping ranges from 339 to 341 feet. The next group, after 341 feet, starts at 342 feet. And grouping them by 3, we have the 342, 343, and 344. And we continue this pattern for the rest of the scale here. So if this group ends at 344, the next group starts at 345, and so on, grouping them 3 by 3 by 3 by 3. We stop when we reach the entire range of the data. That is, once we pass the largest data value in our sample. And by looking through the data value, we notice that the largest stopping distance was 358 feet. So our final grouping in our histogram must include the largest data value, 358 feet. So since the group just before the last group ended at 356 feet, the last group starts at the next data, which is 357 feet, and grouping them 3 at a time, we go from 357, 358 to 359. So now that we've included all the data in our range, we can then count the data, that is, to get the frequency, to complete the frequency scale. So back to our initial or first group, 336 to 338 feet. Looking at all of our 25 stopping distances in our sample, and we go through and count just the autos that took 336 to 338 feet to come to a stop, we see that there is 2, 337 and a 338. So a frequency of 2 vehicles took anywhere from 336 to 338 feet to come to a stop. So that means we can draw our bar in the histogram for the first group to a height of a frequency of 2. So we label it 2, and we draw that bar right over that first group, 336 to 338 feet. And now we do this for each of the subsequent groupings. In a histogram, we draw the bars touching each other because the data is quantitative. And quantitative or numerical data follow this number line, which is a continuous sort of scale. One number turns into the next number and so on. So our bars will touch. And the second grouping that ranges from 339 to 341 feet, we go through and count to find the frequency through all this data, and we'll see that there are 2. There's a 340 foot and a 339 foot vehicle stopping distance. So that's a frequency of 2. So the second category, from 339 to 341 feet, has a frequency of 2. Our next category ranges from 342 to 344 feet. Looking through all the data and counting, we see there's 1, 2, 3, 4. 4 automobiles took a total of 342 to 344 feet to come to a complete stop. So since we've established our frequency scale of counting by 2s, we complete the scale by going from 0 to 2 to 4, and we draw the bar right above 342 to 344 to a height of a frequency of 4. Next, we go through the data and count all the vehicles that took a total of 345 to 347 feet to come to a stop. When we do this, we count a frequency of 1, 2, 3, 4, 5, 6, 7. So we need to draw a bar to a height of 7. Now continuing our scale, which is on the frequency, which is counting by 2s, we have 0, 2, 4, 6, and 8. Since this group has a frequency of 7, we draw the bar to a height that's right between the 6 and the 8, which corresponds to 7. Next, going through all the data and counting the automobiles that took 348 to 350 feet to come to a stop, we count and get a frequency of 1, 2, 3, 4, 5, 6. So the next group gets a bar drawn to a height of 6 on the frequency scale, right above the 348 to 350 feet. Next, going through the data and counting the 351 to 353 stopping distances, we get a frequency of 1, 2, 3. So here we draw our bar to a height of 3, which on our scale is right between the 2 and the 4. Next, when we go through all the data and count how many of the automobiles took 354 to 356 feet to come to a complete stop, we look through and count and find that there is 0. None of the vehicles in this sample took 354 to 356 feet to come to a stop. So there will be no bar drawn above that category. And finally, looking at the 357 to 358 stopping distances, we see that there's just one automobile that took that length to stop. So we draw a bar above the 357 to 359 feet to a frequency height of 1. And on our scale, 1 is right between the 0 and the 2. So here we've completed our answer to part A. We have constructed a frequency histogram with an initial grouping of 336 to 338 feet for this data. We provided a title. We completely labeled the horizontal or data axis, and we completely labeled the vertical or statistic axis. We drew our bars in the histogram to a height corresponding to the frequency, and all the bars touching where we had data. Now we can answer part B. Use appropriate descriptive statistics methods to describe the important characteristics of the data collected in problem 4. There are 3 important characteristics to describe: the distribution, which shows the overall pattern or shape in the data; the central tendency, which sort of measures the average or typical value; and the dispersion, which measures the overall variation or spread in the data. Which descriptive statistic method is appropriate to use depends on the data. So looking at our data, total stopping distance, we see that it is quantitative. And so with quantitative data, it narrows our choices, but not completely. We now have to determine whether our quantitative data contained outliers or not. A data value is considered to be an outlier when it falls 3 or more standard deviations from the mean. So the number of standard deviations from the mean can be determined by calculating a standard score. So one way to determine if there's an outlier is to calculate the standard score for the data values. And if any of the data values have a standard score that is +3 or higher or -3 or lower, you have an outlier. But if all of the standard scores fall somewhere between the -3 and 3, we do not have an outlier. Another way, or a different way of doing this, would be to just calculate the range that cuts off outliers. That is, we could take the mean and then go +3 standard deviations from that mean and -3 standard deviations from that mean in order to find the cutoff where data values fall 3 or more standard deviations from the mean. This could be done by taking the mean and subtracting and adding 3 standard deviations. The x bar -3 s sub x would identify the cutoff for outliers on the below average side. So outliers are any value that are less than or equal to the x bar -3 times s sub x. Or outliers in the above mean side are any values that are greater than or equal to the x bar +3 times sx. So we've already calculated the sample mean and the sample standard deviation in problem 4. So we could use those results to help find the cutoff to identify any outliers. Here we could use the mean x bar of 346.0, rounded off carrying that 1 extra decimal place. And we could use our sample standard deviation sx equals to 5.0, rounded off carrying that 1 extra decimal place. So we could take the mean of 346.0 and then subtract 3, which is the 3 standard deviation cutoff to be an outlier, times 5.0, which is what a standard deviation is equal to. So 3 standard deviations would be, in this case, 3 times the 5 feet. 3 times 5 is 15. So if we go 15 feet below the mean of 346, you would get 346 minus the 15, which is 331 feet. Any stopping distance that is less than or equal to 331 feet would be considered an outlier. For the above average side, we would take the mean x bar of 346.0 plus 3 times s sub x, which is 5.0. 346.0 plus 3 times 5.0 equals 361.0. So any stopping distance that is 361.0 feet or higher would be considered an outlier on the high side. So looking at our histogram, we see that the histogram goes to a low of 336 feet, and none of the data appear in the outlier range, which is 331 or lower. So there's no data that fall in the outlier area on the left. The histogram ranges to a high of 359 feet, and we could see that none of the data go past 359. And so that means none of the data fall 361 feet or higher, which would be an outlier in the above average area. So we have no outliers on the low side and no outliers on the high side. So when we have quantitative data with no outliers, we could use the mean to measure the central tendency and the standard deviation to measure the dispersion. We already have these values calculated from before, so we're ready to continue. As far as the distribution goes, we can use either a distribution table, a histogram, or stem and leaf plot to reveal the distribution or the shape of the data. Since we've already constructed a frequency histogram in part A, we can just look at our answer to part A to reveal the distribution. Here, we see that the distribution follows this low frequencies on the extremes and the higher frequencies in the center. This low, high, low pattern, which is quite symmetric, can be described as a bell-shaped distribution. So the total stopping distance has a bell-shaped distribution based on the histogram we constructed. And then to describe the central tendency and dispersion, we can just use our mean and standard deviation to make that description. So to give an answer to part B, we've already identified which descriptive statistic methods were appropriate, and we've already determined that we have quantitative data with no outliers. So since the total stopping distance involves quantitative data with no outliers, we can use a histogram, the mean, and the standard deviation in order to describe the three important characteristics: the distribution, central tendency, and dispersion of the data. So now we can give our answer to part B, which is a description of the important characteristics of this data. A description is an answer written in words of the problem. So we need to describe these three important characteristics: the distribution, the central tendency, and the dispersion, in words of the problem, which is total stopping distance of vehicles going 65 miles per hour in dry conditions. And since the data was quantitative with no outliers, we're going to use the mean and the standard deviation to describe these, along with our histogram that revealed that the distribution was bell-shaped. So our answer to part B can be given this way. The total stopping distance for automobiles traveling at 65 miles per hour in dry conditions exhibits a bell-shaped distribution with a mean of 346.0 feet and a standard deviation of 5.0 feet. This is just one acceptable description that can be given. Again, you could give an acceptable description of the important characteristics in lots of different ways. That is, you can give the order of the distribution, central tendency, and dispersion, in whatever order you want. Just make sure you use the words of the problem and the appropriate descriptive statistics to complete your description.